Okay, I want to show you some real magic here. Now, I've just taken apart this radio, which is a Panasonic RF562DD2. And this is just real magic. If you want to have real magic in your hands, this is about $5. Just take apart one of these. And I've got this quartz crystal as well. So just to explain why I love quartz crystals, sometimes in radios you find quartz crystals. In most watches, you'll find a quartz crystal. And this has got a property called piezo or piezoelectric. And if you hit this hard enough, it will release an electric current or an electric field. And if you pass an electric field through it, it will actually vibrate. Now, when it vibrates at a very, very specific frequency. So when people say, oh, quartz crystals emit frequency, only when you do something to them. And that's the piezo or piezoelectric effect. So if you basically pass a current through this, it will oscillate at a certain frequency. It will move. It literally jiggles backwards and forwards, depending upon the size and the cut of this piece of quartz crystal. So what people do is they cut this to a very small size and a small angle, and it oscillates if you pass a current through it at 32,768 times a second. If you divide that by 15 times, you get to 1, and that's 1 second on a clock. That's how a quartz crystal works. So I normally look for quartz crystals in radios, because what's more kind of honest than nature? What's going to create a better oscillatory frequency than nature, than a quartz crystal? Nothing, I don't think, until you get to really high frequencies, right? Because these don't oscillate that high frequency. That's when you need to use amplifiers and different types of technology. So that's why I love looking at radios. Now, check out this radio. Now, what's really cool about this is like the dumbest radio ever. None of these integrated circuits aren't proper microchips. They have no coding installed on them. They're basically just dumb analog transistors. That's all they are. And you can see in here, it's all just wind up mechanics, which I love, because this is how you really understand how these things work. So the question is, the thing I'm fascinated by, a frequency. I'm fascinated by radio waves. So how does, something pass through the air, hit this antennae here, and actually allow us to hear, radio voice or whatever. So I don't know if you just heard, but some radio astronomers got together and they got into this old radio telescope in Norway. It sounds like Duolingo. It's like Duolingo, I think is the name of the radio telescope. And they picked up radio waves from Voyager 1, which is 25 billion kilometers away. And I worked out that the volts per meter, the electric field that hit that radio telescope, is about 0.000, so 10 to the minus 20-ish volts per meter. So just imagine 1 volt, right, per meter. Just imagine a volt, and then put 25 zeros in front of it, point zeros. That's how minuscule the electric field is when it hit this radio telescope. And these radio astronomers can pick that up, which is amazing, right? I mean, that's magic. I mean, that's more than that. Sometimes they say that reality is crazier than, Anyway, so how does this work? Now, an electric field hits this. So somewhere there is another radio transmitting on a frequency radio waves, AM or FM, amplitude modulated or frequency modulated. They travel through the air. That's a whole other subject. They hit this antennae, right? They hit this they're like radio waves emit in a spherical way. So they kind of, that's why the radio telescopes, a lot of them are put in a curved way, because they emit spherically. Anyway, so the radio waves hit this. They're not like these two-dimensional waves that you imagine. They're big spheres. Imagine you turn on a light on a torch and the torch gets bigger as it goes out, unless it's a laser. So the sphere of radio waves hit this antenna, depending on the size of it. And depending on the size of the antenna it correlates better with the field, with the size of the electric field, based on the size of this antenna, right? So if you're using a monopole antenna, like just a single thing that hits the ground, you want an antenna about a quarter the size of the wave. But it can be really rough to resonate with the size of the wave. So let's just say this electromagnetic wave comes from a radio station. It hits this, and what it does is, because it's a wave, it hits this. And what does this do? This is just a dumb piece of aluminium, right? There's loads of maths you can do around the aluminium to work out exactly how many electrons are in it and the flow of the electrons. But real simply, all it does is it accelerates electrons up and down this antenna. That is it. I want to keep any video under 10 minutes, like massively under 10 minutes. So all it does, it oscillates electrons up and down this antenna. That's it. That will happen if I put it here, if I attach it to this, if I put it here. That's actually interesting because if this emits, that would be a horizontally polarized wave. And if it emits that way, it would be a vertically polarized wave. And that's all polarization means. Polarization of EM fields is not fundamental. I can change the polarization by doing that. So the field comes, it hits the radio, and it comes through here, and you'll notice it's grounded, but that's a whole other discussion. But it hits this, and this is what I think is pretty cool about this circuit. If you don't have a crystal to oscillate a frequency so that you can put the crystal in here and pick something up on that frequency, there's a load of other ways of doing it, but the most common is called an LC circuit. Just L stands for inductance and C stands for capacitance. So you get a inductor, right, which is a coil, which is the magnetic part, and you get a capacitor, which is the electric field part. So this is literally just a piece of air in the middle, right? Could say, in fact, there's nothing in the middle of the two plates, and there's two plates, and you pass an electric field across them, and you build up capacitance, you build up an electric field. It's called a static electric field. I've done a video on that, actually. It's real simple, and I love building capacitors because they're really interesting. But basically, this stores an electric field. When this takes the electric field from the batteries, it stores it. And as it begins to discharge and release, that's what capacitor does, it discharges into the coil. And the coil takes the field, right? It takes the field. It kind of, it's almost like a slosh, like a spring and a dance between the capacitor and the inductor. The inductor's this coil here. Now, normally you have a coil on the board, but what's really cool is they're just using the coil, which is the same coil which is used to tune the resonant frequency of this antenna. So you just move if you've ever had one of those crystal diode radios, you just move the pin along here, and obviously it changes the frequency, if you've used a variac or anything like that before. So this is attached directly to the antenna, which is attached directly to the coil, which is attached to one of these. I'm not actually sure. I need to look which capacitor it goes to. I'm trying to look at the field, but the PCB lines. But let's just say it's attached to that capacitor. So when this discharges, the field goes into here, which actually creates a magnetic field. This goes through the coil, all the electrons wind through the coil, and when it gets full, all of the electrons go back and fill up the capacitor. Now that goes backwards and forwards, and if you get the inductance exactly right, I'm going to guess, no, I'm not going to guess, I'm going to remember from the sheet, it's around 350 microhenries in this bar, in this ferrite bar, but it doesn't matter too much. Let's not do the maths right now. The maths is really easy. It's like, for an LC circuit, it's super simple. So if you get the capacitance right, and you get the inductance right, you get this beautiful swing flow, nearly, got to finish the video soon, of it doesn't even matter that it's part magnetic and part electric. That's really weird. The magnetic field here is completely wasted, right? But it's creating this swing. And what that swing does is create just an alternating current. And we can put that alternating current through the antennae, or read the alternating current through the antenna. And that is all it is. Like, so if I'm going to emit, if I wanted to transmit from this, I've got some transmitters somewhere. If I want to transmit from this, I just need to create that oscillatory circuit again, put it through here, make the electrons bounce up and down here, exactly the right frequency. That will emit a frequency. And then I just need to use a mixer and put some information on there with either amplitude modulation or frequency modulation. And this will then emit a wave, just like a walkie-talkie. So it's really cool, and it's so simple. And it's like, there's not that many fundamental parts to an EM wave. There's like the amplitude, which is amplitude modulation, which means that when the wave goes, you can change. I don't like doing this with my hands because it's really inaccurate. The amplitude is how much you kind of distort the space around you. So it's shown often in a graph, but a graph is not reality, right? So they show you the higher, you know, the wavelength is in meters, right? So we know the wavelength, right? I've got less than 1 minute left. And we know, okay, so amplitude modulation is the voltage higher and lower. So like say plus 5 volts per meter and minus 5 volts per meter. And the frequency is how close together the wavelength is. And that's basically what a wave is. And that's why it's so simple, but it's so incredible to understand how this works. So this is the radio, a really quick rundown, super basic rundown of a radio. And I wanted to do this quickly for my niece, Isabella.